Okay, in this video we're going to be talking about current, and we're going to be looking at some circuits to see how we apply the current law. Current is the measure of the flow of charges. It's how many charges are flowing by every second, right? So we normally measure charges in coulombs, so it's coulombs per second. We also tend to use amperes and amps, which are the more common units that we use for current, but it says the same thing. If we have 1 amp of current, then that means there's 1 coulomb flowing by every second. All right, so very important to understand with current flow is current is always instantaneous and uniform. So what do we mean? I guess we could start with instantaneous, but they go hand in hand. If I had an electron and it was ready to move through this piece of wire, well, this electron can't move onto this piece of wire until this electron gets out of its way. And this one can't move till this one gets out of its way. And this one doesn't move till this one gets out of the way, and so on and so forth as we travel through the wire until that last electron is ready to jump onto the positive side of the battery. So none of these move until the one in front of them moves. But as soon as that one does, they all move together. That's what we mean by instantaneous. It's not like a hose outside where you turn it on, you have to wait for the water to get to the side of the hose where it's coming out, right? That's not it at all, right? All of these electrons are in the wire, and they all start moving as soon as a circuit is made. The other thing is it's uniform, right? If we have 3 amps coming out of the battery or 3 coulombs per second coming out of the battery, well, then that means on the other side there must be 3 coulombs per second going into the battery. And everywhere else on that path, there must also be 3 coulombs per second going there also. So everywhere throughout the circuit, there's a total of 3 coulombs per second. Now that could split up and recombine in other places, but it still has to be that amount. We can't have 3 coulombs of charges coming out of the battery per second, and then on the other side, only 2 coulombs coming in. That means we lost a bunch of charges somewhere. They disappeared, and that's not possible. And we can't have more coming in, because that means we bred them, or somehow we gained more somewhere. And again, that can't be the case either. So the current has to be uniform. Current flowing in equals the current flowing out. Okay, another important thing to understand about current flow is the direction of current flow. I think I bring it up in almost every electricity video or electrical circuit video, but electrons flow from the negative side of the battery to the positive side of the battery. But that's not really what we're talking about when we talk about current flow. For current flow, we assume the opposite direction, and we're going to be using this assumption for a long time. So every time we talk about the direction of current flow, we are going from the positive side of the battery to the negative side. Some people call it positive flow, which is fine, but either way, we need to understand that when we draw a circuit, we're assuming current is flowing from the positive side of the battery to the negative. Okay, so this brings us to Kirchoff's current law, which says current flow into a junction equals the current flowing out. That's not saying anything drastically different than that current is uniform and instantaneous. We're really saying the same thing here. He's just saying it a different way. And the way that he says it really allows us to make equations for a circuit. We're going to look at all of these, but let's start with this one. So we have 3 resistors. We have resistor 1, we have resistor 2, and we have resistor 3. And I know it has a bunch of V's for voltage, but we don't really care about the voltage for this one. We really are just looking at the current. On the video for voltage, then it matters. So we could pick whatever we want as the junction. I could pick right there as the junction. The current flowing into that junction comes from the battery, so I could say the current of the battery equals the current flowing out, and the current that flows out is going through resistor 1. Notice I don't care what happens after resistor 1 for this junction. But if I make another junction, well, the current flowing in is coming from resistor 1 equals the current flowing out, which is going through resistor 2, so I know those two are equal. And if I pick this as my junction, the current flowing in is resistor 2, and that equals the current flowing out with resistor 3. Now, we really wouldn't need the law if all circuits were series circuits, because just by definition of a series circuit, we know that they get the same current, because a series circuit is a circuit where the charges that flow through the first resistor must flow through the second, and the charges that flow through the second must come from the first. So just by knowing these 3 are in series, we know they have the same current, right? But Kirchoff's current law tells us the same thing. I can pick any junction as I want. I look at what's going in, I look at what's going out, and they have to be the same amount of current. Now that's great. series circuit is nice and straightforward, so let's pick a different one. Let's pick this one here. Now there's different things that are happening because we have multiple paths, right? If you remember, now we have some things that are in parallel with other things. Certainly there's some things in series. So if I'm going to number these, that is 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. So that's what I'm going to number these resistors. Now I could pick some places like last time. If I pick that as my junction, then that says the current flowing in, which is the current of 1, equals the current flowing out, which is the current of 2. I know those two currents have to be the same. If I pick this as my junction, this is a different relationship. Current of 3 must equal the current of 4. There we go. And if I pick one more, because there is one more, the current of 5 must equal the current of 6. So just picking out the series ones. Again, the law tells me it, but also just know when they're in series, right? These three relations have to be true for those. Now, let's pick a different one. All right, so now let's pick a junction, because really the law wasn't made for these simple situations where things are just in series. It was really for where wires split apart or come together, where there is a junction or a division in it, right, or a break in it. So let's pick that one right there. Now the current flowing into that is coming from resistor 2, so the current flowing in is going to equal the current flowing out, and the current flowing in is from resistor 2, and that's going to equal the current flowing out. Now if we watch at the current flowing out, some go up this way, some charges go up this way, some charges go that way. So the current flowing out, well, some of those charges go through 3, and some of those charges go through 5. So that is the statement for the junction that I marked in blue. The current flowing in equals the current flowing out, or the current of resistor 2 equals the current of 3 and 5. Again, I don't care what's happening after 3 and 5. I don't care about what's immediately before and what's immediately after. What happens after that? Well, that's another equation. That's another relationship. Right? So let's look at one more relationship. Let's find one more junction. There we go. And I'm going to pick right there. Right where B is. So the current flowing in, well, the current flowing in is equal to the current of 4. The current through resistor 4 flows into that junction, plus the current of 6. The current of 6 is flowing into that junction, and then it all combines and flows out and goes back into the battery. So I could say that it equals the total current or the current of the battery. And I could also say that the current of the battery is what goes into 1. So I could also say it's equal to the current of 1 or the current of 2 if I want to go a little farther, right? We have all of these relationships. Every single one of them has to be true for this circuit. All right, let's look at one more circuit. Here we go. And for this circuit, it doesn't show the battery, so I'm just going to put it in. Let's assume that the battery is right there, right? So this is just a drawing that I stole. And we don't worry about the equivalent resistance, not what we're looking for. We just put a battery there, and let's say that's our circuit. Now, they're numbered a little weird, but that's all right. They're already numbered, so that's good. And I pick a junction, and I pick this junction right there. The current flowing in equals the current flowing out. As long as you can visualize the flow, you can make the equation. The current's flowing in from here, and then it's flowing out, out, or out this way. Different charges will take different paths. That means I could say the current through resistor 0 equals the current through resistor 1 plus the current through resistor 5 plus the current through resistor 2. So there is one relationship. I'll pick another junction, and I'll pick a junction right there. So if I keep following it, current's flowing this way, current's flowing this way. It's got to flow out somewhere, so it must be going this way. So the current flowing in, the current of 5, there we go, plus the current of 3, so we've got 5 and 3 equals the current flowing out, and the current flowing out is the current of 4. And one more for this one before we wrap it up. That is right there. And Again, following the same current flow that we've been talking about, or following the same path that we've already established. The current of 1 plus the current of 4 equal the current coming into the battery, or the total current. And again, if we wanted to, we could also even say the current through resistor 0, because the current through resistor 0 is getting all of the current, right? So for this circuit, all three of these equations must be true. Now, just to point out the one series circuit, these two are in series with each other. If I put a junction there, it would tell me that the current of 2 equals the current of 3, and that's certainly a true statement. There we go, the current of 2 equals the current of 3, so that statement also has to be true. And again, we don't necessarily have to put the junction down to say that. We can just recognize their series to say that. Okay, so there's some examples of applying Kirchoff's current law and tying it into what current is and how it flows into throughout a circuit.